It's day 6, and I'm trying very hard to conceal my absolute frustration here because, as you can probably tell from the stars, I actually finished the first half of 6. And being a VI user, I'm very used to typing escape to come out of input mode. And while I was saving this, the screen capture away, I hit escape and not return. And so as a result, I lost it. So I'm going to have to re-record it. I am going to try and follow my original path, mistakes and all, but we'll see how that goes. So my apologies if you were looking forward to seeing me do this from clean, but like I say, I'll probably make enough mistakes anyway to make up for that. So let's go into day 6. So we have traveled back in time to the year 1518, and they're searching still through effectively a maze, but they have to be careful because there's a guard in the maze. So we have to work out where the guard will go ahead of time so the historians can search safely. So there's a map of the area we have to analyze. So the current position of the guard is that up arrow there, and obstructions which the guard can't go through are marked by the octothorpes or hash characters. And the rules for the guard movement are, if there is something directly in front of you, turn right 90 degrees, otherwise take a step forward. So here we're going to have the guard going up, 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 until they hit that, and then they're going to go along here until they hit that, then they're going to go down, etc. And then we have lots of pretty pictures of that. By the end of their walk, the guard at some point will leave this area. So they'll basically walk off the side. Here, if you look down here, they come off the bottom on that X there. And when the guard exits, the walk is over. And what they're asking us to do is to count how many different positions on the maze, on the map, that the guard visits. So we have to emulate the path of the guard and work out how many X's will be on the board. And remember that sometimes an X will occur, the guard will be in the same place multiple times. So in this X here, for example, you can see that they will have gone, I don't know which direction first, but at one time they'll have gone past it vertically, and the other time they'll go through it horizontally. But that's still just one X. In this particular case, it says 41 positions, so we have to see if we can match that. So knowing that we're going to need the initial map, let's go and copy that now. Then wander over to our terminal, and we will do a mkdir 06 cd06 n06.rb, and we'll put that map in our data area just because that's, we know at some point we'll need to do that. Okay, so now we have to think about a couple of things. The first is, how are we going to represent this map? And the obvious way to do it is just to have a two-dimensional array. That's probably doable. The problem, though, just from past experience doing all this kind of mazy kind of stuff, is that there's always boundary conditions. So you don't want to be doing things like, if X is greater than width, then don't do anything or whatever, So typically when you're doing a maze, what you do is you put a fence around the actual area. If this was a two-dimensional array, you'd put an extra row at the top, a row below the bottom, and then a column at the start and at the end. That's a possibility. Recently, when I'm doing this kind of thing, I get lazy, and rather than using an array, I've been using a hash. And the hash will be indexed by the X and Y position. The nice thing about a Ruby hash is that if you index an element that doesn't exist, you get nil back. So our fence is there kind of automatically in that it's just the nil value. So let's read that in. Oh no, before we do that, we also have to think about how we're going to represent our position and our direction. I guess the position is fairly obvious. I mean, for the position, we'll probably just use a two-dimensional array of x, y. Oh, thank you, Copilot. Okay, so we'll probably use a two-dimensional array x, y. How are we going to represent the direction? Well, we have lots of different ways. We could just do it like north, east, south, west, But that actually gets ugly when you're trying to work out, okay, where, if I'm going north and I got a particular XY, then I've got to, add to the Y or subtract from the Y or whatever it is. So we have lots of case statements everywhere. I don't like that. Another way to do it, it would be to represent it as a vector of the change in direction at each step. Okay, so if we have the delta X and the delta Y, then if we are moving up, north, then we are not changing the X direction. And we're actually, because we're going to lower indexes, we're going in -1 to the Y direction. If we're going to the east, then that becomes 1, 0, and then just one more. If we're going to the south, we're not moving in the X direction, and our Y direction is increasing like that. So those are a nice way of having the directions, because all we have to do is take the position, add that vector, and you get the new position. So last thing we have to work out is how are we going to do the rotation. You can rotate any vector by effectively doing a matrix multiplication on it. That's way, way overkill for this, because if we look at the patterns here, you can see that we're only going to have 0, +1, or -1 in any one of these positions. We also know that we have to change axes each time we rotate. So if we're going in the Y direction, we'll be going in the X direction after that. So I think pretty clearly we're going to swap X and Y. And it looks like when we do that, we're going to be changing the sign of Y. So I'm guessing that our turn, so a turn of XY is going to result in -YX. And we can play with that and make sure that that actually works. So at this point, we actually have information about how we're going to represent and manipulate positions and vectors. However, that really is nothing to do with the rest of the algorithm. This is just the internals of how am I going to process movement here. In the old days, I would probably write a class that represented, I don't know what, a point that could be moved or something, and that would do some of this work for me. The problem with that is actually you'd need two classes, one for point and one for vector, even though their representations are the same. And it gets a little messy and a bit verbose. So in the new world, what I tend to do is to create a module. And in this case, I'm just going to call it V for vector. In Ruby, if I want to define methods in a module that are accessible directly, I have to do this little bit of magic here called extend self. I got in trouble when I said I did this, and people were saying to me, that's not what you're supposed to do. You're supposed to define a class and make them all class level methods. And it's like, no, this is not a class. This is a namespace that contains methods. So I'm going to stick to my way of doing it. Thank you. Okay, so first thing we need a way of creating a position. So let's take a position that has x, y, and we'll just return that vector. And it turns out that a vector also has exactly the same representation, so we can just cut and paste that. Not a dry violation, by the way. Okay, so let's write something called move. And it's going to take a position and a vector. And we're just going to return. Well, actually, let's decompose those. So we're going to have x, y is our position. And then dx, dy is going to be our vector. And we're just going to return the position that is x plus dx, y plus dy. And finally, we have the turn right. Okay, and that's this business down here. So if we turn right, and again, we'll decompose that vector x, y is going to be no, vector, sorry, minus y x. Okay. Before we go on, just because I'm the master of the typo, so let's go into IRB and play with this. So we'll load it in. Let's start out by creating a position. Let's make it, I don't know, 4, 5. Then we'll have a vector, which is our direction. And let's make it go straight up towards the top, so that we're not moving in the x direction and we're decreasing our index in the y direction because we're starting at 0 at the top. Okay, so now let's take our position and move. And what we're expecting to get is 4, 4, right? There we go. So then we'll turn our vector right. So vec equals v dot turn right vec. Become 1, 0. Now if we moved along the x direction to 5, 4, 6, 4. Okay, so it looks like we have our little turtle graphicsy thing up and running, which is excellent. So next thing, I guess, is we have to read our map in. And remember that we said that we're going to use a hash for that. So let's have def load map data. Remember, that's the thing after the end. We're going to read each line. And we need the number because we have to actually use that as the index. So we're going to say with index do line, comma, this is the y direction. And then we're going to say, take our line, we're going to chomp it to remove the trailing new line. And then we're going to take each character with the index. I think in a pragmatic programmer we call that a train wreck. Do ch, and then the x. So now we're going to save our, or update our map. So we'll say map v dot position x, y equals ch. It would help if we had a map to put it into. So we'll have map equals boom. Then we'll just return our map. Oh, missing an end. Okay, so now we've loaded our map in. So let's go down to the main body of our code. And the first thing we'll do now is to load our map. Okay, if we come back to the actual map itself, this is where the guard starts. And so we need to actually find that position, find where the guard starts. So let's have start equals find guard map. And that's going to be, oh yeah, all we have to do now is to search the values for that up arrow. Yeah. So we do map.h, do pause, and then the character at that position. And then if the character is an up arrow, we return it. We return the position. If ch equals up arrow and so let's just see if we've broken it. pp start. Oop. 4, 6. So let's see. 0, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6. Okay, so we found the guard. Excellent. Now it says the initial direction is up, which means our vector is v dot vector minus 1. So we're going to iterate here until the guard leaves the map. The guard has left the map when our position is outside the boundary of the map, which means that if we index the map with that position, we'll get nil. Okay, so let's write a quick bit of code here that does that. Pause equals start. That's our current position. While map pause. So we have a vector, we have a position. Let's call that vec. Oh, okay, so our new position equals v dot move pause vec. Now, if that new position is one of these guys, then we don't actually make the move, instead we turn. So if map then we want to turn right. Else, we are going to take the position okay. Oh, but we're not recording where we were, right? We should be recording every place we visit. That's what that was, an X character they put in there. Let's go back over here. Yeah, they're using X's. So what we'll do is we need to record the initial position. So map pause equals X. And then down here, any new position. So that's map pause equals X. So in theory, we've now traversed our graph. We've exited. So now we have to show how many squares we've visited. Oh, okay, and that's easy. Map dot values dot count X. All right, let's see what happens now. 50-50, it loops. 100% it loops. Okay, so we've done something wrong here. What have we done wrong? All right, I'll tell you what we'll do. Let's add a little bit of eye candy to work out what's happening here. Let's dump out the map. So we're going to iterate over it, but we don't know how wide it is or how tall it is. So when we load it up here, we're also going to keep track of how wide and how tall it is. So the height is basically the maximum y value. So, and I don't know, it doesn't say that all lines are necessarily the same length. So what we could do here is to say width equals whatever the current width is, or X, and we'll take the maximum value. And okay, this is kind of a little bit tacky, but I mean, why not? We'll actually store those two values in the map as well. They're not going to look like positions because the positions all look like those vectors. So we can just say map width. And the actual width obviously is the index plus 1. Cool. So that's done that. So now we can do dump will be 0 dot 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 map open brackets height dot each to y 0. Okay, so here we're just going to print the individual character. And then at the end here, we're going to put a new line. Okay, well then we're going to get fancy, because back in the day, in the sort of like late 70s, early 80s, all of my work was done on VT100 style terminals, which is where the ANSI escape sequences that you know and love come from. Those are the things that you use to make your prompt have different colors, for example, in the terminal. And let me just see, I'm fairly sure this is true. If I say print backslash O33 escape, open brackets, home the cursor, backslash O33, open brackets 2J, clear from cursor to end of screen. I cannot remember how old I am. I have to work it out every time. But for some stupid reason, I remember those particular ANSI escape sequences. And then, just so this doesn't fly by, I'm going to put a getters at the end here so we can halt it and then just hit return to see the next step and the next step. So here, let's just call dump map. Let's see what happens now. I'm going to make it a bit bigger, I guess. Oh dear. Read position. X, Y. Oh boy. There we go. Okay, so there's our X where the guy is initially. We're moving up. I'm hitting return to get to the next step. Here we're going to stop and turn to the right. Yep, we do. Now we're going to go down. Look at this. This is kind of fun. Then we're going to go across, bump, back up to there, across to there, down to there, up to there, over to there. Okay, so at this point we should have exited. All right, so we're moving correctly, we're just not ending our loop correctly. So let's come back up here and find out why. Oh, that's why. Because we're actually setting the position even if it's outside the current grid. So we just have to say if map pause. Yeah. And let's just comment that one out. If I delete the line, it guarantees I'll need it again. So Ruby 06, it says 41. And back over on the screen, it says 41. So, okay, it looks like we've we've nailed it. Time to go for the big part. If I can. Like I say, I did this before. Oh, here we go. So we go back to the end here, paste that in, save it away. You got to wonder how they came up with these maps in the first place. Must be pretty tricky. We'll run our code. We get 4982. Come back over here. 4982. Oh, look at that. Cool. All right, so now we're on to fresh new territory for both of us. Part 2. Fortunately, they're pretty sure that... Okay, hang on. The historians explain the guards' patrol area is simply too large for them to safely search the lab without getting caught. Fortunately, they are pretty sure that adding a single new obstruction won't cause a time paradox. They'd like to place the new obstruction in such a way that the guard will get stuck in a loop, making the rest of the lab safe to search. To have the lowest chance of creating a time paradox, they would like to know all of the possible positions for such an obstruction. In the above example, there are only 6 different positions where a new obstruction would cause the guard to get stuck in a loop. Okay, so they use an O. So they add an O here. The guard goes up, down, across, down, hits that way, goes across, hits the loop, and then goes back over that path. And then here's another one. They go up, across, down, all the way over there, up over there, up over there. And then what happens? They turn that way. Oh, and then they go back in a loop around here. Okay. So I guess what we're going to have to do is to put an obstruction in every position one at a time and then see if that causes the guard to loop. Now, what makes a loop? It's not just that the guard visits the same cell, because there's quite a few times where the guard will cross their own path. Oh, but if they enter a cell from a particular direction, then they deterministically, if they do it again, then they're in a loop, because going into a cell in that direction will take them down some path, which if it ends back up at that cell in that direction, then they're just going to do that forever. So that's our loop criteria. Cool. All right, so let's go get our original data here. Go back over to our code. Okay, so we'll just check that data's okay. We should be getting, I think, 41 out of this, if I remember rightly. Yeah, okay. So we need to try every single position. So let's write a separate little loopy for that. 0 ... map height. Okay, so for each position, we'll create a little variable to hold it. Okay, so now we can't put an obstruction where there's already an obstruction. So let's say if the map pause equals dot, now we can put an obstruction in place. Oh, now hang on a second. It said something about obstructions and where the guard is. The new obstruction cannot be placed at the guard's starting position. But that's okay because we've got an X at the guard's starting position, so it won't be a dot. Okay, that's cool. So if the map pos equals a dot, then we'll add an obstruction, which is that hash character. We'll go check for a loop, and then we'll say map pos equals dot again. Cool. And checking for a loop, let's loop found. Oh, it needs to know the start. Oh, yeah. Okay, so, oh, and it asks for a count, so okay, so now we have to write loop found, which is basically, we run this guy here, which is the thing that counted how often we were going around, but this time we're just going to run it until we either fall off the map or enter a loop. Okay, so let's call that pos. Okay, so remember we need to work out if we're going into a cell that we've already been into. Okay, so we're going to have this hash, and the key of that hash is going to be a position and a direction, which we're calling V for vector. Okay, so that's going to be the key that we use. So we're going around our map. If we've already visited this position and this what direction? We don't have a direction. Okay, so we need to add a direction here. Remember to add it down the bottom in a second. So if we've already visited that position going in that direction, then we're going to return true. It's a loop. Otherwise, we're going to do what we did before, right? We don't need to update this with the X. We don't care how many it's doing. Okay. And at the end there, if we've fallen off, it's not a loop. We've gone off the map, so it's false. And we need to add our vector to loop found. Oops. All right. If map pos, oh, an end would be nice. And now what? Vec. Consistent naming. Oh dear, oh dear, oh dear. If loop found, what did I call it? Loop count. It's not loop count, it's loop found. And really, it should be a predicate method, shouldn't it? I tell you, I don't normally get this number of errors. Undefined method visited. That's because it ain't a method. Oh, and you know what? I need to set visited. There you go. And we'll be consistent. There we go. So it says it found 6 loops, which I think is what they said here. There are 6 different positions. Cool. All right, let's go for it. What can possibly go wrong? Well, it could loop forever like that. Now, how on earth are we going to debug this? Well, I guess we could start by just putting a dump map in there, but that's going to be enormous. Okay, so there's loop found. How am I initializing that? So I've got an X there, so that shouldn't be putting one over the start position. Just to be on the safe side here, let's just say I don't know that will make a difference. I don't think it should. No. Okay. All right. Just because I haven't got anything else to do, I'm going to move this down where it makes more logical sense. There. I guess what we should do is work out what our position is each time. So let's do a PP on pause here. We'll see whether it's going infinite in this loop or the other loop. So maybe it wasn't looping. Maybe it's just incredibly slow. All right, I'm not going to make you wait for the end of this, so I'll cut this part out. So it finally came up with an answer, 1663. So let's go back over here. 1663. Yeah, that was the answer. Okay, so technically we've done it, but I'm not at all happy with that performance. So let's think about what we're doing here. Here we have a loop that goes through every element in that map, and it's roughly 10,000 elements. And then for each of those, we're then going to traverse the map. We exit as soon as we find a loop. So my guess is that we're not going to optimize exactly what I've got here too much. The optimization will come from finding a different algorithm. And I'm not too sure I'm up for that right now. So I'm going to check out saying that, yeah, we've done this. I'm not very happy that what we've come up with here is a fairly naive and fairly slow algorithm. There must be a better way. I'm just not too sure I can see it right now. If I do, I will post something. If one of you comes up with something that's like, you know, oh, you idiot, you should have done this, please let me know. And meanwhile, I'll see you on number 7. Take care.